quantum clocks are the most precise clocks that we have, and actually that is what we use to, distribute clocks in the planet, and you need to synchronize very well computers and airplanes and all sort of things that we need very we for our instruments we need very precise ways of measuring time, and these are done by atomic clocks. So very roughly how would an atomic clock work is that you have many atoms here, for example strontium, trapped in an electromagnetic potential. So the sample could be like atoms that are cold, so that means they move very little, and they're within some sort of volume, so typically it's like a millimeter and so on. So the energy levels, the internal energy levels of atoms are very sharp. So let's say between the ground state and the excited state, the energy is very precise. So that you can use this as a frequency standard that gives you like the ticks of the clock very precisely. So you shine a laser and you excite the atoms and so on. And well, that's more or less what you use. So there was this beautiful experiment done many years ago by Dave Wineland, who got the Nobel Prize for trapping ions in an ion trap. He did this experiment after, in which he would take an atomic clock and then sort of put another one or just like move his clock upwards. I'm not sure actually what he did, but he demonstrated time dilation at 33 centimeters. So before we know, okay, we can see time dilation if we're in the Earth and then in a satellite. We know that. But now he said, look at these scales of 33 centimeters. You can see time dilation already.
And that time dilation is just due to the gravitational potential difference?
Yes, due to the Earth. Just from the gravitational field of the Earth. So basically, you're demonstrating that the space-time is curved.
Yes.
No? So that's really amazing. And so, these clocks are super precise. They have like a systematic uncertainty of, they can reach 10 to the minus 18. That means that the error is 1 part in 10 to the 18. So that would be more or less like in years. I used to have it here because I forget, but the clock would lose precision would lose 1 second in something like 30 billion years. I had the number here exactly, but I now lost it. But more or less, not that precise they are. And that's what I was telling my colleagues in general relativity that found it funny that I wanted to measure this curvature things. I said, no, look, I mean, these things are so precise, that is not unthinkable that we can actually measure general relativistic effects at very small scales. So I was talking to Patrick Gill. So he's a colleague of mine who works at the National Physics Laboratory. So that is like the institution in the UK where they do all these, with the Metrology Institute, where they do all these standards of frequency and the different units and so on. So he's working with the quantum clocks, with the Helen Margolis and so on. And I was telling them, you know what? Soon you're going to have a problem because you're going to get the proper time at the bottom of your sample with the proper time at the top is going to be different. And he was saying like, yeah, but we're not too worried about this now. And so 6 months later, that happened. 2 papers came out showing that, they could see time dilation. Well, first there was like this 1 centimeter and then even in 1 millimeter.
Wow.
So now if you think about the quantum clocks, the clock in the atoms in the bottom see a proper time different from the atoms on the top.
Yes. Super interesting.
But okay, still, people working on clocks might not be that worried.
When did this result come out?
That must have been a couple of years ago.
Okay, so fairly recently, 2020s?
Oh, yeah. Yeah.
Wow.
Maybe this is actually... Look, this is from this paper I put here is one of the papers, and it says published in 2022. I think it might have been submitted in 2020 or 2021, but it was published very recently.
Sure, it's still cutting edge. Yeah. I see.
So, okay, so it is not a problem as long as the atoms are independent, because then what you can do, which is what we do with time dilation with GPS, is like we know how that changes, so we can theoretically correct for it, and then you just take that into account, and you don't have a problem. Okay, but now people want to make these clocks more precise and beat this 10 to the minus 18 uncertainty by entangling the atoms. Because we've showed in quantum metrology that if you have entangled atoms, you get, a precision, instead of going like 1 over square root of n, it's 1 over n. It's called the Heisenberg limit, and this makes things much more precise. Okay, so if you do that, then you have a problem. Then you bang your head with quantum mechanics and general relativity being incompatible. Why? Because what time are you going to use? The proper time is going to be different in different heights, and the Schrödinger equation on the left-hand side is like d and dt, an absolute time. So here you have a relative time different at each height. So which time you want to use? Okay. So again, the experimentalists say, "Oh, we're not worried about it at all, Yvette, because we just use the time at the center of the trap." That doesn't work that well, and it's like it's a patch, but forget about it. Let's say maybe for what they want to do, it's good enough. I don't know. But from a theoretical point of view, this is not the right thing to do. But you're actually losing on the possibility of learning what we should be doing, because this is really a very good example where you are at these stages where quantum mechanics and general relativity interplay, but we don't have a theory to describe that experiment. So what I was telling, I recently went and visited the group at NPL, at the National Physics Laboratory, and I was having a little discussion about this, and I was telling them, that we don't have experiments to address these questions, and now you're having an experiment that actually is getting there. So let's use this experiment to try. So you have a theory. That's good. The theory is that you're using is that you say, well, I can more or less do with taking the proper time at the center of my, of my sample. Well, if you want to be rigorous, really what you have is that you lost your notion of time, of clock time, and you need to come up with a new thing. But that is what opens the opportunity of, You came up with a theory which is not very good, I think, which is measuring at the center.
Well, you mentioned theoretical problems, but it sounds like what you're describing is more akin to missed opportunities for probing the interaction of general relativity with quantum theory.
Yes, both in a way, right? I mean, what I was trying to explain to them is that as a theoretician, we don't have a proper theory to explain your experiment. Now, your experiment is an experiment. An experiment is the experiment, right? It's like, in that sense, it's not wrong. What is wrong is the theory that we're using to describe your experiment, but you need to start somewhere. Again, the little circle that we talked about. So I start with a theory that's not very good. Then you do the experiment. We looked at the experimental results, and then I come up with a way of modifying my theory. Yeah. So right now I have a PhD student working on this problem that I like very much. And we've made some progress before, not with atoms, but with light. I want to show you more or less what we did before.
Please.
So Einstein came up with this idea of the Einstein light clock. So he used this clock, this idea of a clock, to argue things for relativity and so on. So he considered two mirrors and then a photon bouncing back and forth, and that gave you like the tickings of the clock. And then he talked about what happens if you move this clock and so on. But now we can use quantum field theory and quantum optics to quantize the idea of Einstein's clock. So I've done that. I wrote another series of papers in that direction, is to say, okay, now I have two mirrors, but I have a quantum electromagnetic field inside. So I get when you do that, you get sort of the field you can write down as an infinite sum of different modes. So those are like states that are sharp in frequency, but the photons are completely delocalized in your box. But you can use quantum field theory to describe that. So that was also like a long journey, because when I started to work with that, you could only do this in flat space. And the only motion that people could describe was a sinusoidal motion of the walls. And this was like the dynamical Casimir effect. But I wanted to do more than that. I wanted to consider curved space from the Earth to a planet and send the little box up to study how the curvature, the underlying curvature of the Earth would affect the quantum clock, or how would like an interplay of quantum states with time dilation would look like, and all that sort of thing. And gosh, that was really, really hard, because solving those equations was very complicated. And what allowed me to make progress was working with Jorma Luco, a colleague in Nottingham, where I used to work, who is an expert in quantum field theory and curved spacetime. And then, we managed to come up with a new methodology where we could now start, let's say, solving those sort of problems in a more general way. And then I had a student and a postdoc that helped me generalize this to curved space and so on. And then, so we have a clock model, which is basically Einstein's light clock, but with a quantum field. We fix a frequency, and the oscillations of the quantum states of this frequency mode give you like the ticking of the clock. But now we can move that in curved space and ask questions about the interplay of time dilation with quantum things. And we found some interesting things, like when you move the clock, due to things like called the dynamical Casimir effect, you create particles like photons inside the clock, and these affect time dilation.
Interesting.
So it's kind of fun doing that,
Yeah.
Again, I don't think you go to the very fundamental questions by doing it, but it's you start learning certain things. And one of the things I was interested in is that, if you use these clocks to measure space and time, or time dilation and so on, because the state of the field is a quantum field, then you start getting into these uncertainty principles, things that you can actually not measure space and time with infinite precision. Like if you measure time very precisely, then space is not, and this sort of thing. So I wanted to explore more the, let's say, the constraints that you get by in measuring space-time by using a quantum system.
Usually when people speak about Heisenberg's uncertainty, they're talking about position and momentum, and you're talking about space and time.
Well, I mean, you could, they don't go together, no? So you have energy and time, and then momentum and position.
Yes.
But in these clocks, you have sort of an interplay of things. You have states that are obey minimum uncertainty in space and momentum, so they're called Gaussian states, coherent states. And then we move these in space, and then you have constraints that come also from the energy and the time. So I didn't kind of go into much detail. I wasn't very precise when I said that. But you started getting the role of the different uncertainty principles that you get from quantum theory, playing a role in how well your clock works and things like that, which is very interesting.
To stay informed in an ever-evolving landscape, I see The Economist as a wellspring of insightful analysis and in-depth reporting on the various topics we explore here and beyond. The Economist's commitment to rigorous journalism means you get a clear picture of the world's most significant developments, whether it's in scientific innovation or the shifting tectonic plates of global politics. The Economist provides comprehensive coverage that goes beyond the headlines. What sets The Economist apart is their ability to make complex issues accessible and engaging, much like we strive to do in this podcast. If you're passionate about expanding your knowledge and gaining a deeper understanding of the forces that shape our world, then I highly recommend subscribing to The Economist. It's an investment into intellectual growth, one that you won't regret. As a listener of TOE, you get a special 20% off discount. Now you can enjoy The Economist and all it has to offer for less. Head over to their website, www.economist.com/TOE, T-O-E, to get started. Thanks for tuning in, and now back to our explorations of the mysteries of the universe.